In this lesson, we will look at the sources of air for an aircraft's cabin air conditioning system, and we will examine the methods used to maintain the air at a satisfactory temperature. We will begin, however, with a short review of the makeup of the atmosphere, to explain the need for air conditioning and pressurization systems. Modern jet airliners cruise at high altitudes, up to 43,000 feet. The advantages of high-altitude flying are greater fuel efficiency, higher speed, and, on most occasions, the aircraft will be above any bad weather. The disadvantages are that there is insufficient oxygen to breathe, and the air is extremely cold. In a standard atmosphere, the temperature drops at a rate of 1.98 degrees per 1,000 feet up to the tropopause, which is at approximately 36,000 feet or 11 kilometers. This means that on a standard day at 31,000 feet, the outside air temperature will be a chilly -46 degrees Celsius. The atmosphere is made up of 78% nitrogen and 21% oxygen, with the other 1% consisting of various trace gases. The pressure of the air at sea level on a standard day is 14.7 pounds per square inch, or psi. So the partial pressure of the oxygen will be 21% of 14.7 psi, which is 3.08 psi. The table here shows the air pressure drop with altitude and the consequent reduction in the partial pressure of the oxygen. Below 10,000 feet, the body can cope with the reduction in oxygen pressure with no harmful effects. Above this height, the effects of hypoxia begin to become apparent, although passengers sitting and relaxing will suffer few noticeable effects below 15,000 feet. Aircraft air conditioning and pressurization systems limit the maximum cabin altitude to 8,000 feet, with a cabin temperature of about 20 degrees Celsius, thus providing a comfortable environment for the crew and passengers without the need for oxygen, except in emergencies. The provision of air from a large gas turbine-engined aircraft's air conditioning system is subject to regulatory requirements, governing both the amount and the quality of the air to be provided. These requirements are laid down in the EASA Certification Specification for Large Aeroplanes, CS25, Book 1. To summarize the regulations, each passenger and crew compartment must be ventilated, and each crew compartment must have enough fresh air, but not less than 0.28 cubic meters per minute, or 10 cubic feet per minute per crew member, to enable crew members to perform their duties without undue discomfort or fatigue. Carbon monoxide concentrations must not be more than 1 part in 20,000 parts of air. Carbon dioxide concentration during flight must not exceed 0.5% by volume in compartments normally occupied by passengers or crew members. Most modern gas turbine-engined aircraft have a bleed air system, which takes hot pressurized air from the engine's compressors and feeds it into the bleed air duct. The air comes primarily from a low-pressure source, but it may be augmented by high-pressure air. On the ground prior to engine start, air may be supplied by an auxiliary power unit. One of the primary uses of this air is to supply the charge air for the aircraft's air conditioning system. Since the bleed air supply is always at a higher temperature than that required for passenger comfort, it needs to be cooled before use. The cooling is done by the air conditioning pack. In order to provide redundancy, there are 2 or more packs, fed from different sections of the bleed air duct. The bleed air flow into the air conditioning pack is controlled by a pack flow control valve. Closing this valve will shut off the airflow and close the pack down. In many installations, this valve modulates to supply a constant mass flow of air to the pack, or in some systems, there is a separate mass flow controller. Most air conditioning packs use an air cycle machine, or ACM. The machine uses the principle of energy conversion and surface heat exchange for its operation. There are three basic types of air cycle machine: the turbo compressor, or bootstrap, the brake turbine, and the turbo fan. We will now look at each of these in turn. Of the three, the turbo compressor or bootstrap is the most popular air cycle machine in current use. It is used where the pressure of the bleed air is relatively low, as in the case of aircraft using high bypass ratio or small turbo propeller engines. It consists of two heat exchangers, both using ram air as their cooling medium, and a rotating turbine and compressor arrangement. The turbine assembly is sometimes referred to as the turbo refrigerator. The low-pressure bleed air, or air from a blower, is pre-cooled in the primary heat exchanger. Although the heat exchanger is very efficient, it can't cool the charge air down to a temperature lower than that of the ambient ram air, which in some situations may be as warm as 40+ degrees Celsius. The cooled bleed air then has its pressure and temperature increased by the compressor. Between the compressor and the turbine is the secondary heat exchanger, which serves to remove from the air much of the heat generated by the compressor. The pressure in the air is then used to drive the turbine. This removes the energy from the air and causes a large temperature drop. The output air temperature from the unit can be as low as 2 degrees Celsius. In order to provide sufficient airflow across the heat exchangers when the aircraft is on the ground, or at low speed in the air, a fan is provided. This fan is normally driven by the turbine, but in some cases it may be electrically or pneumatically operated. The ram air inlet and exit doors control the flow of cooling air through the heat exchanger. Their positions are controlled automatically by signals from the temperature control system. They are normally held open for maximum cooling on the ground and at low speed and low altitude. After takeoff, once the flaps are retracted, the doors will modulate as required to maintain the required pack outlet temperature. In some systems, they are automatically closed during takeoff and landing, to prevent debris damaging the system components. As the aircraft climbs, the outside air temperature cools, allowing the heat exchangers to become more effective. The temperature control valve allows hot bleed air to be added to the cooled air in order to maintain a comfortable cabin temperature. In the brake turbine system, the bleed air pressure from the engine needs to be considerably higher than the pressure required by the bootstrap system. The charge air is supplied directly to the turbine via a heat exchanger. The turbine drives the compressor, which takes in low-pressure ambient air and expels it through a restriction. This causes a back pressure on the compressor, which in turn puts a load of brake on the turbine, hence the name, and provides the energy conversion which removes the heat from the charge air. Some installations feed the output from the compressor into the ducting downstream of the heat exchanger to increase the airflow through the heat exchanger by jet pump action. This system is lighter than the bootstrap system, but unless the jet pump installation is used, it cannot be used for cabin cooling when the aircraft is stationary. The fan turbine, or turbofan system, is a refinement of the brake turbine unit, in which, instead of a compressor, the turbine is coupled to a fan of sufficient capacity to draw the required volume of cooling air through the primary heat exchanger. Therefore, the unit is not dependent on ram air for its operation and can be operated on the ground. The general design of the unit is such that it is extremely light and compact. The engine delivery pressure must be higher than for the other systems, and the turbine must be capable of higher speeds to achieve the necessary pressure drop. That is the end of the lesson. These are the main points that you should now know and understand. The charge air for a modern airliner's air conditioning system is supplied from the engine's compressors. Normally the low-pressure compressor, but in some circumstances the high-pressure compressor may be used. On the ground prior to engine start, air may be supplied by an auxiliary power unit. The temperature and the pressure of the air are controlled by the air conditioning system. The bootstrap is the most common type of air cycle machine. In this system, the charge air is first cooled in the primary heat exchanger. From there it passes to the compressor, where its temperature and pressure are raised. The purpose of this is to ensure an adequate pressure, and thus temperature drop, across the turbine. From the compressor, the air then passes through the secondary heat exchanger, reducing its temperature again. The air is now used to drive the turbine, which in turn drives the compressor. The pressure drop across the turbine produces a large temperature drop. The pack cooling fan is used to supply the heat exchangers with cooling air on the ground and during low-speed operation.